Hello, welcome everyone. It is August 20th at the stroke of 0 UTC on the 21st in 2025, and it's Active Inference GuestStream 118.1. We're here with Tadahiro Taniguchi, and we'll see a presentation on co-creative learning via Metropolis-Hastings interaction between humans and AI, and then I will read any questions in the live chat and ask some things about this fascinating research. So thank you for joining again, Tadahiro, and to you for the presentation.
Okay, thank you very much for inviting me to this great guest stream again. So I'm Tadahiro Taniguchi from Kyoto University. Today, I'll be talking about co-creative learning via Metropolis-Hastings interaction between humans and AI. And this is based on our preprint, which is recently available on arXiv. So this is the co-creative learning. It's a new theory of human in the loop machine learning method. So I also discuss collective predictive coding hypothesis, which I talked in the previous guest stream. Maybe you can check it later. But as a background of this work. Okay, let me start. So here is an overview of our main contributions of this paper. The first, we formally propose co-creative learning. This is a novel paradigm where human and AI collaboratively achieve symbol emergence. In other words, the formation of the external representation by mutually integrating their partial perceptual information to build shared representation. So this fundamentally shifts the perspective on human-AI alignment or teaching process, moving beyond traditional unilateral approach. The second, we introduced an experimental framework based on the Metropolis-Hastings naming game. Through this framework, we propose the comparing empirical evidence demonstrating that human-AI pairs can effectively engage in this co-creative learning process. So the visual of this slide illustrates the idea of mutual interaction between the human and the AI centering around the shared world. Okay. So let's consider why co-creative learning is so crucial currently in this at this phase. So the first one is limitations of unilateral alignment or teaching. Traditionally, unilateral alignment framework or teaching typically supervised learning based on ground truth labels provided by human annotators have significant limitations. For instance, AI systems already excel beyond average human performance in many areas, possessing distinct and often superior domain knowledge. Furthermore, the human and AI inherently have heterogeneous knowledge. Our ways of understanding and processing information are fundamentally different. So when embodied AI agents start exploring the world autonomously, it becomes questionable whether we should enforce our existing human knowledge and values as a sole ground truth. So we should respect, in some sense, we should respect AI's perception and our knowledge to bring our knowledge better status. Okay, another thing is the bidirectional, the inference. So actually, the large language models, for example, actively impact the human language use and decision-making, as shown by recent studies. So the mutual inference clearly highlights the limitation of the perspective of a purely one-side alignment strategy, teaching strategy. Therefore, looking beyond the current generative AI era, it is important that we establish a new system theory, the principle, and learning method to achieve true human AI symbiosis, considering bidirectional alignment or teachings. That can be called co-creative learning process. So, to position co-creative learning more intuitively from the machine learning perspective, let's briefly and roughly review existing traditional unilateral machine learning frameworks. So, in the most common, in supervised or reinforcement learning, the human's perspective, human perspective can be written like that. The XN human is the human's observation, and SN is the kind of the class level or description of the human's perceptual information. So we form in our society we form the relationship between the labels and the perceptual information in some sense. So, and this is effectively serves as the ground truth or the target or reward, the source of reward for the AI to learn from. The AI's understanding is therefore fundamentally bounded by the human's perspective. So, in contrast, in unsupervised or self-supervised learning, the AI agents learns in isolation, inferring knowledge solely from its own observations. In this case, its understanding is bounded only by the limits of its own perceptual data. So a key takeaway from both these traditional approaches is that the only partial information is a human or AI is used for the learning process. So this highlights a critical limitation. Neither approach fully leverages the combined potentially richer the information available when humans and the AI interact. So this brings us to our proposal, the new bilateral frameworks, co-creative learning. Here, the goal is not for one agent to teach the other, but for both to engage in bidirectional message passing through language games and communication to integrate their partial observations. So instead of treating one agent's perspective as a sole ground truth, the learning target for the dyad that becomes the true posterior distribution conditioned on the joint observation of both agents. Here, X and AI and X, the human. This is crucial distinction. So by integrating their distinct and partial information, this approach allows the emergent shared understanding to surpass the knowledge and perception that either the humans or the AI could have formed alone. The diagram on this slide illustrates this mutual interaction and the formation of a joint, more complete understanding. So, how can we do this? That is a question. And before diving into today's main topic, let me briefly introduce or review the collective predictive coding hypothesis, which I proposed last year and gave a talk in this GuestStream last time. So this hypothesis extends the idea of well-known predictive coding to social and linguistic phenomena. So it states that symbol systems, including language, are formed through collective predictive coding by humans. In other words, a human society, which can be regarded as symbol emergence system, the systems performing symbol emergence, that technically can be understood as a social representation learning system. As a result, the information of the world may be encoded in the distributional semantics of our language. The hypothesis also suggests that this is why large language models appear to understand the world. They inherit this structure through vast amount of the distributed human-generated text. By the way, the diagram illustrates this complex process, where the individual inference and action loop contribute to an emergent, the symbol system that in turn constrains the organized's collective behavior. So let me illustrate. So maybe the explanation was too quick. So let me illustrate the CPC hypothesis, collective predictive coding process, the bridging the idea of emergent communication and predictive coding or free energy principle. First, let's start from the predictive coding or word model learning. So there is a person. He or she internally has internal representation of word models. And we are living with action perception loop. So this is very roughly speaking, the inference process. But with humans, we are so many, and through communication, we form language. So following a predictive coding hypothesis, through language game, we can form language-like social, external representations through the total learning process. I think through this process, we model and adapt to the world collectively. So, but here, let me take another view. Until now, we assume that each person is an independent and autonomous agent. But let's change and take another viewpoint. First, language is here. Language is a kind of autonomous system. And they have sensors or also actuators. That's us. The language utilizes us to model the world through interaction. From this viewpoint, we are subordinate to the language system. So this kind of view is often mentioned in sociology or other social science area or cultural psychology. So I think this kind of dual viewpoint is very interesting to extend our view of cognition to the social viewpoint. And actually, this dual viewpoint actually gives us opportunity to formalize this process from the viewpoint of free energy principle. So, based on the generative model representing CPC, I mean this kind of the language model. Let's consider a language is a kind of brain having these sensor model systems. So the following the graphical model, the probabilistic generative model, the describing such kind of process, we can define the free energy in the same way as the usual, the free energy principle. Interestingly, that we can, we can naturally derive this kind of formulation. And interestingly, the final form can be divided into two parts. So the first one is an ordinary variation of free energy term. And this is a sum of the variation of free energy of a number of agents. In addition to that, an interesting term pops up. We call this a collective regularization term. This term tries to align agents' external representations, W, and with each agent internal representation, Z. With this term, the problem of minimization individual free energy becomes a minimization of free energy of a single total system. I think this view can extend the free energy principle from the individual to the collective level with a clear relationship to the emergence of symbol systems or language. Okay, so as the simplest instance of the theory of collective predictive coding, let me introduce the Metropolis-Hastings naming game, which we previously proposed. It is a type of language game built on the solid mathematical foundations. This will serve as a basis of co-creative learning. I will introduce later. Okay, how does it work? So here's the outline. First, in the perception phase, the speaker and listener observe the same object and infer their internal representations. We assume joint attention here, which is crucial for human language acquisition. Next, in communication phase, the speaker probabilistically utter a name for the object. The listener then determines if it accepts the naming, or not, with a certain probability. The probability depends on its current belief state. Specifically, this probability shown in the equation on the slide reflects how well the listener's belief matches the name proposed by the speaker. So if the listener agent does not find the incoming sign believable, it can reject the proposed name. This ability to reject is crucial. The third, the learning phase. After the communication, the listener updates its internal parameter related to representation, learning, and naming. And finally, in turn-taking step, the speaker and the listener alternate as their role, and the game continues. Overall, this is a very, very simple game. But importantly, this game has a solid mathematical basis. So let's dive into the detail. If the acceptance decision is made according to this probability, we can mathematically prove that the naming game is equivalent to the Metropolis-Hastings algorithm for Bayesian inference of the shared representation that shown in this figure on the left. So let's begin with this graphical model. So here, OA and OB, or we can rename this XA or XB, that represents a visual observation of each agent. They are the agents with the visual input here, but any kind of input is okay, basically. ZA and ZB are the internal representations, latent variables. We also assume the existence of a variable W, which serves as a prior for these two observations, two internal variables. So if we treat W as a latent variable, this graphical model becomes very similar to the multimodal or multi-view variational autoencoder or latent variable models. And if the two agents' brains were directly connected, and could use the both observations simultaneously, yes, this variable can be inferred in the natural way and would encode the combined information from both agents' input. However, in reality, they are independent cognitive systems. So let's introduce a trick. Algorithmically, we can decompose the model into two parts. So left-hand side are agent A, and the right-hand side is agent B. So and let's consider the kind of the alternative, the inference, the method for this W. Now think about the sampling process. Agent A propose a candidate of latent variable WD by sampling from its posterior distribution. And the proposed value is passed to agent B. The agent B can decide whether to accept the sample from a sample based on certain probability. So this process is this process can be designed by using the Metropolis-Hastings algorithm, which is a kind of Markov chain Monte Carlo, MCMC. So actually, under certain conditions, this guarantees that shared signs are formed and that categories emerges among the agent to approximate the posterior distribution based on the agent's observations. So, and importantly, what I explained here is completely equivalent to this naming game. So it is proved that this naming game itself is Bayesian, the inference, approximate Bayesian inference procedure. So this is a very important point. So in the previous paper, we tested this idea on some dataset, and we showed that two agent playing Metropolis-Hastings naming game can effectively integrate the perceptual information and form and share signs. I mean the categories, across the agent. And actually, such kind of process even outperform the learning result achieved by a single agent. So, without any ground truth, this kind of Metropolis-Hastings interaction can improve the representation learning process. In some sense, the knowledge, the formation process. Okay, so this is the background. And actually, after this computation study, as you saw in my talk, I always assume that this is something happening that in our society, human. So to show that, we need to validate that if this kind of things is happening in human interaction. So we designed an experiment to test whether a human participant, when playing a game similar to the Metropolis-Hastings naming game, would follow the acceptance probability calculated by the algorithm. The results, as shown in the graphs on the right, are positive. So we found that the human acceptance behavior indeed mostly aligned with the theoretically derived MH acceptance probability. This is a crucial finding because it suggests that humans, to a certain extent, follow similar patterns to the Metropolis-Hastings naming game, providing empirical support for the idea that human behavior on simple emergence might follow a CPC mechanism. This paves the way for our recent work, integrating AI and human into this framework. So this is the beginning of actually today's main topic. So a simple way to introduce co-creative learning is to view it through the lens of a Metropolis-Hastings style interaction between human and AI, like this. So, okay, let's jump into this section. So given this insight, we then move to the core of our current work, the realization of collective predictive coding within a human and AI collaborative system. As depicted in this graphical model, we envision a system where a human and AI agent, each with partial observations, engage in bilateral message passing through language game or communication. This interaction facilitates the formation and inference of a shared representation, and represented by the QSN. This is the kind of sign and shared latent variable, and XAI and X-human. This means that AI's observations and humans' observations. Okay, this is what we define as co-creative learning. The key idea here is that instead of one agent simply teaching the other, the both mutually integrate their partial perceptual information. The display process enabled by the mechanism like the MHNG, Metropolis-Hastings naming game, allows them to jointly construct a richer shared external representation that neither could achieve alone. This is a direct instantiation of the CPC hypothesis in a human AI triad. So more formally, to be precise, we formally define co-creative learning as an interactive, decentralized Bayesian inference process, as shown in definition 1 in our preprint. Through message-based update, like the Metropolis-Hastings naming game, jointly construct local belief distributions. The crucial aspect is that this process ensures the expected collective free energy, FT, decreased over interaction steps. This means that the Markov chain formed by their interactions converges to the true posterior distribution conditioned on joint observations of the both AI and the humans. So what's remarkable about this mechanism is that it allows for improvement of Monte Carlo estimates of the evidence P XAI X human, without requiring either agent to disclose their private observation or internal gradient. So this decentralized nature is a key advantage in enabling robust and private knowledge co-construction. Okay, so with this formal definition in mind, our primary objective for this experiment was to empirically test this concept. We conducted an experiment where a joint attention naming game. This is a kind of the experiment with participants to asking to play the MH naming game like naming game. So this game was played between human participant and the computer agent. The central question we aim to answer was, can the human and the computer effectively integrate their respective partial observations through this naming game? So thereby, they engage in the decentralized Bayesian inference, or as we term it, co-creative learning. To ensure this, each agent was given only a partial missing subset of the full observational information. As you can see in this diagram, the human might have certain dimension of features, and while the agent has others, and some are missing for each. So this setup makes accurate categorization impossible based solely on individual information, thus necessitating information integration through communication. We wanted to see if they could collaboratively fill in these missing pieces and reach a shared understanding. So let's detail our material and methods. The stimuli consisted on images depicting circle with a radial notch. So these were generated based on 5-dimensional vectors sampled from one of 3 ground truth Gaussian distribution. And using the CIE lab color space, which is perceptually uniform. So the parameters were chosen so that categories would overlap significantly in the partial observation space, like this. Crucially, as shown in figure, this part, humans and computer agents receive different partial observations. Human participants view grayscale rendering based on the original figure. And yeah, okay. And the agent only can see the color information. This partial observability makes accurate categorization impossible based solely on individual information. So making communication essential. So the dyad's task was to collaboratively categorize these stimuli into up to 3 categories. The ABC. By playing the naming game. This side, figure B, illustrates experimental procedure flow, involving initial categorization, and the naming game, turn and role switching. So this is actually very difficult task for human participant, as you can imagine. Okay, this is this is the process. The slide shows a screenshot of the experimental interface used in our experiment. First, participants were asked to categorize the given images by dragging them into labeled boxes, as seen on the left. During the naming game, one image is presented on the right. And the naming agent propose a name or sign for the imaging by clicking the button. The listener then decide whether to accept the proposed name by clicking and accept or reject. Sorry, the instruction is in Japanese. After this decision, the listener is prompted to revise their own categorization if needed. This intuitive interface supports the partial observation and the sign exchange between the human and the computer agent, facilitating the interactive process. Okay, so the experiment was conducted online via web browser. We recruited 90 participants through CloudWorks, crowdsourcing service, and after filtering for engagement and adherence to instruction, 69 participants were included in our final analysis. The experiment typically lasted about 90 to 120 minutes, like 2 hours. With participants receiving compensation for their time. Okay, so for comparison, participants were divided into 3 distinct groups. So each interacting with computer agent, employing a different acceptance strategy for human proposal. Group 1, the MH group, the Metropolis-Hastings, engaged with an AI that accepted the proposals based on the Metropolis-Hastings acceptance probability, serving as our primary co-creative learning condition. Group 2, the always accept group, that interacted with an AI that always accept proposals, acting as a proxy for traditional supervised learning. The human's suggestion is always true. Finally, group 3, the always reject group, communicated with an AI that always reject human proposals, the mirroring an unsupervised learning scenario. So the AI just learn the form categories from their observation. These conditions allows us to systematically evaluate the effectiveness of the MHNG in facilitating co-creative learning. So let's look at the result for clustering accuracy measured by adjusted random index ARI. Table 1 summarizes the initial and final mean ARI score for both human and computer agents across all groups. A key finding is that the participants in MH group achieved the highest categorization accuracy and sign agreement, particularly on the AI side. When compared to both the always accept and always reject group. Specifically, the computer agent in the MH condition, a computer agent in MH condition achieved a significantly higher final mean ARI. This clearly indicates that the MH-based interaction most effectively facilitated shared understanding between human and AI, engaging a more collaborative and accurate modeling of the world. So while interacting generally helped the human improve, the MH mechanism was uniquely effective for the AI agent to leverage the interaction for superior performance. Okay, to visualize this trend, in this figure 3, plots the mean ARI over the 200 communication steps for both human and computer agent in the condition. You can clearly observe that both the MH and AA are always acceptance condition show a general trend to increase ARI for both humans and computer, indicating successful information integration and learning from interaction. And in stark contrast, the AR condition always reject condition, where the AI always reject proposal, show little to no improvement from the initial categorization accuracy, especially for the computer agent. This graph vividly demonstrates the superior performance and the learning trajectory achieved under the Metropolis-Hastings interaction, particularly for the AI agent. Okay, beyond just categorization accuracy, we also evaluated the sign posterior distribution convergence. So as highlighted in table 1, the MH group achieves the highest convergence between the agent's final sign distribution and the target posterior distribution derived from the combined model. This indicates that the MH-based interaction most effectively guided the dyad towards the emergence of a shared informative sign system that truly reflect the integrated information. While human participants in the MH condition also show the high agreement, the difference compared to the always accept condition was not statistically significant. So, however, the AI's performance in the MH group was significantly superior, demonstrating its ability to converge the interaction to align its understanding with the humans, leading to a richer shared representation as indicated by the convergence toward the S given XAI and XHuman. To summarize our discussion, our experiments clearly show that the human AI pair can successfully engage in co-creative learning via the joint attention naming game. So, under partial observation, the Metropolis-Hastings acceptance rule significantly improve categorization accuracy and agreement that compared to both always accept and always reject control conditions. This is evident in the ARI graph, and the sign agreement score we just discussed. Furthermore, a crucial finding was that the human acceptance behavior aligned closely with the theoretically derived Metropolis-Hastings probability, as shown in figure 4, this figure. This reinforces the idea that the mechanism enhances perceptual integration and effectively facilitates decentralized Bayesian inference within human AI dyads. So these findings collectively suggest a promising direction of the designing truly symbiotic AI systems that run with human by fostering the emergent, so interaction-driven alignment, moving beyond the limitation of the traditional unilateral approach to AI development. Okay, so while our findings are highly promising, we acknowledge several limitations in our current studies that we utilized actually simple, the artificially generated visual stimuli and categorical signs. So this control setup was necessary for initial validation, I believe, but it naturally limits the generalizability of our findings to complex real-world tasks involving richer semantics and natural language, such as those handled by large language models. So additionally, our joint attention naming game paradigm assumes a perfect joint attention between agents. So in real-world interactions, so attentional alignment can fail, which is an important aspect for future research. And looking ahead, we identify several key future challenges. These include scaling to richer modality and semantics, robustness to imperfect attention, designing real-time co-adaptive system, and understanding emergent dynamics in large-scale systems, and also ethical and interpretability concern is also important, I think. So, and actually, to build a truly symbiotic human AI society, so how to integrate this kind of idea to the practical applications? That is also important topic. Okay, that's all from my side. Thank you very much for your attention, and I look forward to further discussion. Okay, thank you very much.
Thank you for the talk. Awesome. All right. I will ask a few questions that I wrote, and I will copy them into the chat as well. And for anyone in the live chat, please feel free to write questions and I'll copy them in. All right. So first comment and question. The task focused on categorical discrete as well as quantitative aspects of situational semantics, played via a language game related to sharing information about a shape in a shared world. What kinds of AI human tasks do you think this kind of algorithm could be used for? For example, do you see it in the domain of the text chat or a robotic setting? Or just, in other words, which application directions do you find promising or most able to demonstrate the differences and strengths of the framework compared with the unilateral supervised or unsupervised learning systems?
Yeah, thank you very much for great questions. There actually that I should ask, I should add in our explanation. So actually, maybe this experiment itself looks very how to say simple and categorical sign formation. And what I want to show in this talk and in this paper is the kind of the basic validation of this approach, co-creative learning. So, and this this graphical model and this setting is not limited to the categorical setting, and also the small number. I mean the simple visual image. And actually, so as I mentioned, what I did is swapping the one agent in this the kind of the naming language game, the swapping swapped by a human participant. So actually, this kind of approach, collective predictive coding based approach, is now the extending to many domains. So let me share so it's a kind of appendix slide. So actually, this approach was extended to the multiple agent and also the multi-agent reinforcement learning. And also importantly, this is also another preprint we recently shared. So this approach can be extended to the more complex tasks. So this is, for example, this paper is dealing with the kind of the captioning game, not the naming game, captioning game. So between the two vision language model agent, the one agent receives a natural image and describe it in natural language. Okay. So then another agent receive the text. Text is just a vector, vector a sequence of categorical variables, and that can be treated in our framework in a similar way. So actually, we showed that this kind of process successfully integrate the two agents, the knowledge of the vision language models. So I think many research is now ongoing. So I think that I believe we can extend this idea to the large language model setting. And also that we can, say that now, as you know, currently in robotics field, vision language action model is gathering attention. So maybe we can consider how can we extend this idea to such kind of robotics scenario as well.
Awesome. Okay. Next question, and then I'll read from the chat. Okay. How do you see this in terms of converging to a shared stable truth versus situations of novelty like co-creation of art or research, where there's not necessarily a pre-existing ground truth, even of a latent kind, to converge to? I'm thinking about situations where the agent models have overlapping information, which is redundant, though robust, or non-overlapping information, which is useful, though fragile, and then also information that maybe neither agent has. Mm-hmm. So how do you adapt the situation to tune whether you're looking to kind of find an existing compromise versus move into a third space that might be different than what either agent has or knows?
Thank you very much for your great question. And actually, that's very, 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 very interesting topic and interesting discussion point. So actually, mathematically speaking, so if they don't have the shared information, I mean the observation does not contain shared the information, So it's very difficult to, I expect that it's very difficult to form the shared representations and reach agreement in some sense. So, and it's very, but I don't have the empirical evidence about that on with some experiment. But I think that this is now, it's very important step to conduct constructive studies to analyze what kind of phenomena happens with this kind of basic mechanism of symbol emergence and formation of shared the representation. And also now, maybe this is a kind of somehow a bit outside of today's topic. And I think that this kind of scenario can be found in the democratic discussion in our society as well. So I think that one of my students is working on the topic about the relationship between collective predictive coding and democracy and digital democracy. So if the two agents don't have the shared experience, it's very difficult to reach agreement. And also if they have a very different belief system, it will become very difficult to agree. So that's such kind of thing. This kind of mechanism is somehow existing behind the curtain of the current social division or system. Yeah, I think that currently I'm very interested in the connection between this kind of computational research and symbol emergence, representation learning things, and social science topics as well. Thank you very much.
Yes, that makes a lot of sense. I guess just speculatively, if two agents are in a shared environment with a simple optima to be reached, or at least a gradient to be followed, at least there's a norm to which the gradient could be followed, or local or global optima could be reached. But if you have agents that are in two different environments, you kind of lose even the possibility of a guarantee. Because if two people are in two different rooms with two different temperatures, there's no guarantee they would converge to the same air conditioning. But if they were in the same room with a shared air conditioning, at least they could. Yeah. Okay. Yeah, go ahead.
I think it's very interesting to think over the kind of how can we improve the design of communication, and how should we consider the difference of environment to achieve the mutual to understand the mutual understanding between two or more agents, something like that. Sorry.
Yeah.
Sorry.
I'll read a question from the live chat. If anyone else has a live chat question, they should write it. So Frederick Quintanar wrote, in your model, how do you approach the difference between the way silicon agents and humans model the concept level of words and context? AI is opaque. How can this be improved for interpretability?
Okay. Thank you very much. That's also a very much important point. In our framework, the most important part of our framework is that we totally deal totally deal with a system, a kind of decentralized system. So one of the most important part of this mechanism, each agent need not look into the internal phenomena of the counterpart agents. So even in the computer agent settings, what the agent A do is just a kind of utter the giving sign to speak something and listen and determine if it accepts or not by itself. So there is no, there is no need to kind of look into the other agents variables, So this, actually, in the similar studies in emergent communication, many studies, ask agent to pass the kind of the gradient of the parameter through agents, So across agents, it's impossible for human. But in this setting, we don't need to do that. So actually, in this mechanism, we just consider the kind of counterpart agent as a black box. So what we did in this framework is in concrete learning is just swapping the black box by human agent and just expect the human behavior follows the MH naming game-based mechanism algorithm. So actually, to that end, to validate that, so we conducted this experiment previously, and we somehow found that the human, in this kind of setting, human actually followed the MH algorithm to some extent. And also in this experiment again, we checked that the human behavior is similar to the MH algorithm. And as a result, that we can expect that the total, the collective free energy can be decreased through this interaction. That is a scenario. And regarding the explainability, that is a very, the difficult question, and we need to consider. And in the series of studies of explainable AI, so the definition of explainability is, very somehow uncertain, the fragile. And actually explain, even in the current large language model, the explainability, what's happening inside of the neural network is a very challenging problem. And the human, I think the similar problem can be found in this scenario as well. But anyway, so when we introduce this kind of idea to our society, we assume that AI is not just a follower of students of human. So the human decision can be affected by AI. So maybe, of course, that we need to reconsider the ethical issues and explainability based on such kind of assumptions. Sorry, my answer is not perfect, but yeah, that's comment from my side.
Great. Okay, and one more question I wrote in a comment in the chat. So,
Okay, thank you.
You mentioned different ways of communication amongst AI, and human-human dyads and groups. And I think the relevance of understanding and modeling and creating high-integrity settings for these communications is clear. So what might these communication strategies look like? For example, let's assume that we can do real-time language translation between mother tongues like Japanese or English. From there, what kinds of games might be possible? For example, would that high bandwidth communication still look like, how are you doing? What are you up to? Or could there be some structured communication games like captioning or joint classification, which could engage shared attention in ways that were previously impossible and discover new global free energy optima?
Thank you very much for your questions. I'm now Hanse and try to grasp the point. We can do real-time language translation. Let's assume mother tongue, like from there, what
Like,
kind of game?
if everyone could speak and hear in the natural language that was most comfortable to them, what would be the semantics of the language games that would support high bandwidth communication?
High bandwidth communication. You mean so what does the real-time language translation means here? So everyone can, this means everyone can understand what the other.
You can speak in Japanese and hear what I'm saying in Japanese, and I'll hear what you say in English, and I could speak in English. So we're using some AI system to auto translate what we hear and say in close to real time, so that so we can have a natural conversation with our mother tongues. So then I'm just kind of curious and wondering whether then we would have a sort of normal, like, on the street conversation, or whether your work is providing some situations or structured games, like kind of like language chess, where we could play a game together, like captioning or classification, that could be used to reduce the free energy on a joint distribution in a way that would be like faster or different than just asking about your day or your friends or your family.
Thank you for your question, and I'm not still sure if I get the point clearly. But basically MH naming game or captioning game. This is kind of a very very small subset of what's happening in our total language game in our society. So actually basically our assumption is that our assumption or our idea is that the language, the formation of language or symbol emergence itself is a part of the adaptation to the environment. And, that's totally somehow same as the predictive coding and active inference. And so so I don't have a clear answer to this question, but how to say? So we share some task. We share some task or some environment. If we are human, the task. So maybe gradually our way of communication gradually change and optimize to the shared task or shared environment. That's my idea, and I don't know I don't know the connection with the real time translation. How to say the discussion point. So, is it okay? I don't know.
Yeah,
Sorry.
I think it's a mystery for us and others to explore in the future. Like, if we were fluent in hearing and speaking to everybody, what would we talk about? Like if we knew every language perfectly and we could communicate to everyone and everyone could be included in the conversation, would that conversation look like just meeting somebody at the bus stop? Or I think your work provides some structured settings where the information content of communication could be quantitatively analyzed and different contributions and proposals could be understood in terms of how they contribute to co-alignment. Okay. And
thank you very much.
Yes. Last question. So what are your next research directions or questions? And what milestones or developments from your group and colleagues or in the broader AI space are you looking out for?
Okay, thank you very much. In the relation with the development of AI system, so the one thing is that how can we integrate this idea into LLM, the agent systems, and the VLM and the vision language action model, and actually, so one of the basically the CPC, the original idea is CPC and the simple emergence systems. So I would like to jump out from this kind of agent viewpoint. But I think that this is crucial to consider how can we form the language system or shared the belief system together with other agent. I think it's crucial for human intelligence, I think, and cognition, I think. And from this viewpoint, I think we can integrate the human and AI and robot to this system. So, and that can bring us to the next step of AI, human and AI, the symbiotic society. So that is the important point. And the first one step is to make this kind of system work with AI and robot. I mean I showed the VLM, the image captioning game system. So actually that improve the performance of VLM. And also that I think that LLM can be let's say the kind of the decentralized or multi-agent LLM system can be reformulated from this viewpoint. And also, we can put the human agent to such kind of ecosystems, So of course, the human LLM interaction can take time, and through that process, so LLM can learn from the human participants, adaptively, but at the same time, so inevitably human agents can be affected by LLM's output. But in many discussions, this kind of the phenomena is regarded as just a bias. Or bias, somehow, the bias is tend to be considered as a negative thing. But, such kind of bias, it can be regarded as a kind of the knowledge from AI agent as well. So I think that one of the most important next step is to formalize this kind of interaction from the viewpoint of the collective free energy minimization and language, MH-like language game, and produce the kind of qualitatively different the human AI the system, and that hopefully guarantee the co-creative process. That is the most important step to forward. Yes. Thank you very much.
Thank you. A great way to end it. I really appreciated the presentation. I think that the comparison of supervised or unsupervised learning makes it clear that both of the unilateral frameworks have fundamental limitations, and that a co-creative path is a great joint distributional future.
Thank you very much.
Thank you. Okay, till next time. See you.
Thank you very much.